Previous algorithms learned patterns using equations or collections of decision trees. Support vector machines take a different approach. Instead of building many rules, SVM searches for the single best boundary that separates different groups. Imagine separating cats from dogs using measurable features. There are many possible boundaries, but only one provides the greatest confidence for future predictions. The separating surface is called a hyperplane. In 2 dimensions, it appears as a line. In 3 dimensions, it becomes a plane. In higher dimensions, the same idea still applies. SVMs do not simply separate the classes, they search for the boundary with the maximum margin. A larger margin generally makes the classifier more robust when encountering new data. Real data is messy, so practical SVMs use a soft margin. They tolerate a few points inside the band in exchange for a wider, more reliable boundary. Surprisingly, the entire decision boundary depends primarily on just a few critical observations. These special data points are called support vectors. They define the position of the optimal boundary. Some datasets cannot be separated by a straight line. SVM overcomes this challenge using kernels, which transform the data into a higher dimensional space where a simple separating boundary becomes possible. During training, the algorithm searches for the hyperplane that maximizes the margin while minimizing classification errors. The optimization continues until the best solution is found. Let's recap. An SVM classifies by drawing the single best boundary. Best means the widest margin between the classes. Only the support vectors, the closest points, decide where that boundary sits, and kernels handle data no straight line can split. Support vector machines excel when data is limited but features are informative. They have been widely used in medicine, image recognition, remote sensing, cybersecurity, and industrial automation. Support vector machines classify data by finding the best boundary, but another algorithm takes an entirely different approach. Instead of geometry, it relies on probability. In the next episode, we'll explore naive Bayes.